Today we're jumping into one of the greatest scientific detective stories ever told. Seriously, it's a tale packed with mystery, a few brilliant clues, and one incredible mind who saw a connection that would literally change the world as we know it. All right, so let's set the scene. We're in the 19th century. Think gas lamps, steam engines. And scientists were totally fascinated by two strange and powerful forces that seemed, well, almost magical: electricity and magnetism. They were cool for sure, but everyone believed they were completely separate things. And that really brings us to the central mystery we're going to crack today. What could possibly connect something as huge as a lightning strike, the simple, quiet pull of a magnet on your fridge, and the very light coming from the screen you're looking at right now? The answer, it turns out, is absolutely mind-blowing. So on one side, you had electricity. It was the stuff of static shocks when you touched a doorknob, weird sparks in labs, and this newfangled idea of a current flowing through a wire. And then, over here, you had magnetism, that invisible force that makes compasses point north and makes certain metals stick together. They just seem to operate in totally different ways. Two different worlds. Or so they thought. But just like in any great mystery, clues started to surface. Over a few decades, a handful of brilliant scientific detectives each uncovered a crucial piece of the puzzle. A law that described exactly how one of these forces behaved. So let's break down the 4 key clues they discovered. So the first clue is called Gauss's law. And really, the core idea is pretty simple. It basically says that electric charges, the tiny positive and negative particles, they're the source of electric fields. The more charge you pack into a space, the stronger the field radiating out from it. To make this super clear, just picture a faucet. An electric charge is like that faucet, and the water pouring out, that's your electric field. A bigger charge is just like cranking the faucet wide open. You get a much stronger flow. Makes sense, right? All right, clue number 2 takes us over to the world of magnetism. And this is where things get different. While electricity starts with charges, Gauss's law for magnetism says there's no such thing as a magnetic charge. Magnetic fields don't have a start or an end point. They just form these continuous closed loops. And you've definitely seen this in action. If you take a bar magnet and you snap it in two, what happens? You don't get a separate North Pole and a South Pole. Nope. You just get 2 brand new, smaller magnets, and each one has its own North and South Pole. You can never, ever have one without the other. Okay, now this is where the plot really thickens. Clue number 3. Faraday's law was a total game changer. It says that a changing magnetic field, and that's the key word here, changing, can actually create an electric field. Boom! All of a sudden, these 2 worlds that everyone thought were totally separate had a bridge between them. And look, this wasn't just some weird lab trick. This is literally the foundation of our entire world. Every single power plant that's powering your lights right now is basically just spinning magnets near coils of wire using Faraday's law to generate electricity. So, a changing magnetic field makes an electric field. But does it work the other way around? You bet it does. That's our 4th and final clue, Ampere's law. It's the perfect flip side to Faraday's. It says that an electric current, that flow of charge, doesn't just sit there. It creates its own magnetic field that wraps right around the wire. You can see this so clearly in that classic classroom experiment. You run electricity through a wire, bring a compass nearby, and what happens? The needle moves. The electricity is creating a magnetic field right there in front of your eyes. The link between the two was absolutely undeniable. So there we have it. 4 major clues all sitting there on the table. But it took one guy, the master detective of our story, a Scottish physicist named James Clerk Maxwell, to see how all the pieces fit together and finally crack the case. And here's the thing about Maxwell's genius. He didn't just gather up these laws. He studied them so deeply that he realized, wait a minute, something's not quite right here. There was a subtle inconsistency. So, with a moment of pure mathematical brilliance, he added one final crucial term to the equations to make everything work perfectly. And the result of his work was, well, it was breathtaking. A set of just 4 beautifully symmetric equations. And what they proved was that electricity and magnetism weren't just related, they were 2 sides of the very same coin. A single fundamental force of nature, electromagnetism. The case was closed, or so he thought, Because hiding inside those four equations was a secret, a prediction. When Maxwell started playing with his new, complete equations, they revealed something so unexpected, so profound, it was about to change science forever. His math showed that if you wiggle an electric field, it creates a changing magnetic field, which in turn creates a changing electric field, and so on. And this creates a self-propagating wave. And when he calculated the speed of this wave, using only numbers from experiments with electricity and magnets, he got this very specific value. Now, that number, 299,792 kilometers per second, might seem random, but Maxwell knew it wasn't, because he knew that physicists at that very time had been working their tails off to measure the speed of light. And their best measurement was almost exactly the same number. I mean, it was a dead ringer, too close to be a coincidence. The conclusion was just inescapable. In his own words, Maxwell realized that light itself is an electromagnetic wave. This wasn't a coincidence. This was a flat-out revelation. And that was the stunning twist ending to our whole detective story. Maxwell set out to understand electricity and magnetism, and in the process, he accidentally stumbled upon the true nature of light, solving a mystery that had puzzled humanity for thousands of years. This discovery wasn't just some beautiful piece of theory to be filed away in a library. It unlocked a new world. This understanding that you could create and control these electromagnetic waves is the single most important foundation of our modern technological society. I mean, think about it. Radio waves, microwaves, the Wi-Fi signal you're probably using right now, the data streaming to your phone, all of it. Every single bit is just a different frequency of the exact same electromagnetic waves that Maxwell's equations predicted. His theory is the invisible backbone of our entire connected world. So here's the real takeaway. That 19th century theory isn't just history, it's happening right now, all around you. The text you just sent, the network your computer is on, the GPS guiding you home, it's all a direct application of Maxwell's elegant unification of two mysterious forces. Maxwell's incredible success inspired generations of physicists, including Einstein, to go hunting for even deeper connections. And that quest is still going on today. Physicists are trying to unite electromagnetism with the forces inside an atom's nucleus, maybe even gravity itself. It really makes you wonder, doesn't it? What's the next great unification going to be, and how will it change everything all over again?